Let me start. So today we'll be talking about a series, or which is the same thing, infinite series. So basically what we'll try to do is, so on R we have seen that we have a binary operation, addition, right? Which means that given any two reals, you have a third real which you get through this operation. And by repeating this, if you have, let's say, finitely many elements from R, then you can also talk about their sum. So you don't have to worry about brackets because of associativity. So this is basically essentially repeating the binary operation on two elements at a time. Now what we'll do is we'll try to give meaning to an infinite sum. So we have, in fact, I'm sure you have used infinite sums. We applied them somewhere or the other. Now, how to give a precise meaning to this? So that is what a series is about. So for this, in addition to this operation, we also need a topology which we now already have on R. So we have these open sets, and we have also now learned about sequences and their convergence. So you simply define such a sum to be the limit of these things whenever it exists. So in other words, when you're looking at a series, you are essentially looking at a sequence which is of this special form. So let's say you have a sequence of reals. Then you talk about, so this is a notation. You talk about a series whose nth term is an. But when you're talking about this, your primary object of interest is the sequence Sn, where Sn is this. Okay, so these objects all make sense just because you have this binary operation and you have associativity, and then you are looking at whether this sequence converges. If this sequence converges, then you say that this series converges, and so on. So this essence, they're called the nth partial sum of the series summation n. So just one thing. So here I have said I've started with a sequence of reals, which means we had this sequence of reals, and then we talked about this series, which means the nth partial sum would be this. So you can, in your notation, you can specify that if you want. So instead of just writing this summation sign and n, you also write this as this, where you specify this. And it becomes important when sometimes you you need to look at another series whose initial term is not A0, but let's say A3, next term is A4 and so on, in which case this would be the series. So in this case, your partial sums, those would be, the first one would be A3, the second one would be A3 plus A4. The next one would be A3 plus A4 plus A5 and so on. So primarily it's just a language. So there's nothing new. Now that we know about sequences, we are actually looking at sequences and their limits. It's just that the focus is on these here, which are slightly different. So we are interested in the limits of these objects, but these things you are writing in this form. So just like for sequences, you say that a series converges to, let's say, S if limit of Sn is S. So this sequence Sn has a limit and is equal to S. The definitions diverges to plus infinity if limit of Sn is plus infinity, or diverges to minus infinity if limit of Sn is minus infinity. So let's look at a few examples. So let's say that means we are looking at this series. So what would be the nth partial sum of this series? So it is the sum of the terms up to the nth term. So this you can sum. So what is the expression? So what can you say about this series? Does it converge? Does it?
Diverge to plus infinity.
Diverge to plus infinity. So this now let's look at another series. Let's say this. So here, what is the nth partial sum? So what is it going to be?
Either 0 or 1.
Right. It would be 0 or 1 depending on. So if n is even, it is 1, odd. So in this case, what happens? In this case, none of these happen, right? Essence do not converge, essence do not go to plus infinity, essence do not go to minus infinity. So, sorry. Does not have a limit. what about this series? So it is the sum of these terms up to n. So this sum you know. I mean, we have not talked about this in this course, but you are familiar with this, right? It's a geometric progression. You know the expression. So what is it? The sum?
So it will be 1 times
Yeah.
1 minus 1 by 2 whole to the power n, I think.
N plus 1.
Yeah. Divide by 1 half, divide by half.
Right. So this is 2 times 1 minus so what happens to this series? What can you say about this series? Which is, you can further simplify. This is 2 minus 1 over 2 to the power n. So as n grows, what happens?
Converges to 2.
Right. Because 1 over 2 to the power n, that goes to 0. So Sn goes to 2. So this series converges. This series converges to 2. Okay. So we'll slowly come across more and more complicated series. So for that, now let's go to some of the properties. Okay. So first thing to observe is the following. So one of the things that we'll be concerned with is, given a series, whether it converges. Okay. Now, suppose we have a series that converges. That means Sn. So assume that converges. And if you just look at the definition, so this is where we call the series converges. So in this case also it has a limit, but we don't say that it converges to plus infinity, converges to minus infinity. We'll say that it diverges to plus infinity or diverges to minus infinity. So so here we are in the first case in the definition. So this essence converge to some real. Okay. Now, if you look at the nth term, if you write them in terms of the essence, essence, the partial sums. So what is it? An is Sn minus Sn minus 1. And you have assumed that Sn converges to S. So this goes to S. As n goes to infinity, what happens to this? This also goes to S, right? So you think of this as one sequence, this as another sequence. So Bn goes to S, Cn goes to S. So where does An go to? This is 0, right? So if your series is convergent, then you must have this, that the nth term must go to 0. Nth term must converge to 0. So this is a necessary condition for a series to converge, right? If you, for example, if you are given a series and you immediately observe that the nth terms do not go to 0, then you can conclude that does not converge to any real. So that is one necessary condition. Okay. So let's say that's first observation. Next, let's say you have a series and let's assume that these are all non-negative. So in this case, what can we say about the sequence of partial sums? So this is A0 plus A1 plus AN. What is Sn plus 1? Sn plus 1 is Sn plus the n plus 1th term. And this is non-negative. So the sequence of partial sums in this case is increasing. Okay, so in such a case, what do we know? We know quite a bit about its limit, right? Its behavior, the behavior of the sequence Sn. So what can we say about this?
Bounded below.
Sorry, repeat again.
It is bounded below.
Okay. Because the initial term, every subsequent term is bigger than that. Okay, that is one. Anything else?
It converges if it is bounded above.
Right. So for monotone increasing sequences, we know that if it's bounded above, then it must converge. So if Sn is bounded above, then it converges. And what happens if Sn is not bounded above?
Diverges to
Right.
infinity.
Right. So what are the possibilities? There exists M such that, so this is exactly the condition that it is the sequence Sn is bounded above. So in this case, summation An converges, and the other possible case is that not bounded above, in which case Sn diverges to plus infinity. So once you have a series with non-negative terms, really the only thing you should, what you should immediately try and verify is whether the partial sums are bounded. If they're bounded, it will converge to a real. You may not know what that real is. You may not be able to write down a formula, for example, but there would be a real to which it converges. And if the partial sums are not bounded above, then it would diverge to plus infinity. So for such series, there's no other behavior you will observe. Just these two cases are possible. And okay, so here just one remark. So just like sequences, we have seen that when you are talking about limits, limit points, all these limiting notions, the initial few terms do not matter. So here also you can check the following. So I have said this for series of non-negative terms, but if you have a series for which, except for finitely many terms, all the terms are non-negative, that means after a while all the terms are non-negative, even then whatever we have seen here, they will continue to hold. So the partial sums will not be increasing throughout, but after a stage they will be increasing, and then everything else will be the same. Okay. So and you can have a similar statement for series with non-positive terms. So there you have to, the sequence of partial sums would be decreasing. So you have to worry about whether it is bounded below or not. If it is bounded below, it would converge. If it is not bounded below, it would diverge to minus infinity. So this would follow from the earlier statement if you look at this series. Okay.
Sir,
Yeah.
over here, like bounded below
Hmm.
would be equivalent to the limit of an approaching 0.
No, not equivalent. It would imply that ans approach 0, but it is not equivalent. So we'll come to that. So I'll just mention it now. We'll see it later. If you look at this series, okay, which means Sn is 1 plus half plus up to 1 over n plus 1. Okay, so here nth term you can see that it goes to 0, right?
Yes, sir.
But Sn
Does not converge.
not bounded above. Okay.
Yes, sir.
So we'll come to this later on. So they're not equivalent. So that, going back to the first condition again, I'll repeat, this is a necessary condition. So the implication works in this direction, but the other direction is not correct, not true. Okay. Now, suppose you have two different series. Let's say this converges to A, this converges to B. Then you can also, of course, talk about this series, where the nth term is just the sum of the nth terms of these two. So then this will also converge, and this will converge to A plus B. So this would follow from the corresponding property of sequences. The nth partial sum of this would be nth partial sum of the first series plus the nth partial sum of the second series. So it would just follow from that. So that's one basic property that you can immediately get from that of sequences. Then okay, so what happens if An converges to A and Bn diverges to plus infinity? So basically you are dealing with, if you look at the partial sums, so let's say Sn is the partial sums of the first series, Tn's are the partial sums of the second series. Then what you are given is Sn goes to A and Tn goes to plus infinity. So again, it reduces to a statement about sequences. And in such a case, Sn plus Tn goes to
A plus
Plus
infinity.
and that is plus infinity, if you recall. So on when we introduce those extended reals, these statements, I think I had mentioned, right, that the statement about limit of sum of two sequences, those continue to hold as long as this plus this makes sense. Here it does. So this implies summation n plus bn diverges to plus infinity. So I'll write it as an exercise so that you can write down a proof, complete proof. Similarly, converges to A, summation bn diverges to minus infinity, imply summation n plus bn diverges to minus infinity. So again, you write down a proof. The proof again would follow from the corresponding statement about sequences. What is a more problematic case is this. Okay, no, first let me take care of this case, diverges to plus infinity. Then also there's no problem. So again, this is another statement which won't be difficult to prove. The case where there's no clear answer is this. Okay, so here nothing definite can be said about summation n plus bn. And why is that? So that for that we can just look at some examples. So let's say let's look at this example where an is n. This example we have seen summation n. So here summation n is plus infinity, right? You take bn to be minus n. Then what is an plus bn? N plus bn is 0. So in this case, summation an is plus infinity, summation bn is minus infinity, but summation an plus bn converges to 0. Let's look at another example. So we'll just distort this example a little bit. N, bn equal to minus n by 2, let's say. So summation an is plus infinity, summation bn is minus infinity. That these conditions hold. But when you look at an plus bn, that's n by 2, which means this diverges to plus infinity. Okay, so it is possible to have this converge to something. It is possible to have this diverge to plus infinity. And I mean, from this example, you can see that you can do just about anything that you want. So like here, if you make it minus 2n, then this series will diverge to minus infinity. And similarly, from here, let's say you take a n to be this, bn to be minus n plus, then summation an plus bn. An plus bn is going to be minus 1 to the power n. And we have seen that that series, whose nth term is minus 1 to the power n, that does not converge, does not diverge to anything. Okay, so it does not have a limit. So in this case, there's no definite conclusion possible. All kinds of things can happen to their sum of the two series. Okay. The other property, suppose this is a series that you are looking at, and this converges to A, and lambda is some real. Then if you look at the series whose nth term is this would converge to lambda times A. Again, this is simple to prove. This would be simple to prove, so I'm not getting into the detailed proof here. What happens when this diverges to plus infinity and lambda is a real?
If lambda is non-zero, it will diverge.
Right. So here you have to make a distinction between these two cases. So if lambda is non-zero, then what happens? Where will it go to?
The sign of lambda.
Right. It would depend on whether lambda is positive or negative. So, I mean, sign of lambda times plus infinity, meaning, right? Infinity you cannot forget.
Yes.
So diverges to plus infinity if lambda is positive. If lambda is negative, this diverges to minus infinity. And if lambda is 0, again, there's no definite conclusion possible. And again, you can look at examples for that. You can construct examples. No, sorry. What happens if lambda is equal to 0? Sorry. What I was trying to say is not for this case. So what happens when lambda is 0?
Converges to 0.
Converges to 0 because all the terms become 0. So it's simple enough. Yeah. So so there's no problem in this case. Okay. And you have a similar statement if summation an diverges to minus infinity also, and that is clear enough. I mean, in that case, also essentially the feature would be that if lambda is positive, it would diverge to the same thing, that is minus infinity. If lambda is negative, it would diverge to plus infinity. The sign would get reversed. Okay. So we have looked at sum of two series, scalar product with this. So you can now say something about this also. So this would be combining the two earlier cases. So, I mean, once you know about the behavior of summation n and summation bn, you know about the behavior of summation minus bn, and then you can say something about, I mean, you know how this would behave. So for this, what would be the case that would be problematic, where there won't be any definite conclusion?
Both diverge to plus infinity.
Right. So both diverges to the same infinity, that is either both diverges to plus infinity or both diverges to minus infinity. So that is the case where you cannot say anything definite, and that basically we have from this example, just by a slight modification, you can produce examples that would tell you that there's no definite conclusion possible. Okay. Now let us look at this series. So just one specific series to begin with, and then see. So what are the partial sums? Partial sums are, so S0 is 1, S1 is 1 minus half, S2 is 1 minus half plus 1/3, and so on. And when I say and so on, let me write down what is the nth term. So 1 minus half plus 1/3 minus, so the last term would be so in this case, can we say anything about the behavior of this series?
So can we separate this into like the sum into two different sums?
Then,
So say we take all the positive terms together and all the negative terms together.
okay, here you mean?
Yes.
Okay, do that then.
So then maybe we'll be able to. So say 1 plus 1/3 plus 1/5.
Okay.
So that will be a sequence of, so that will be a sequence of 1 upon. So what will this sequence be? 1 upon the odd number.
That is true up to some stage, yes. But then what?
Then we use the an minus b thing maybe.
No, but yeah, but what do you know about these?
So both of these converge. So yeah, both of these converge to 0.
Sorry,
Both of these converge to 0.
do they?
So like the individual, like so 1/3, these converges to 0. So
But not these sums.
No,
Sums.
not the sum. Yeah.
Okay, maybe okay. Just briefly. So since we did not see what happens to the partial sum of this series, so let's just look at that first, and then I'll come back to this example. So here, what is Sn? Sn is 1 plus half plus 1/3 plus up to 1 by n plus 1. Okay. Now, I had mentioned that this does not converge, but do you know of a proof? Can you tell me why? I mean, I'm just asking in case you have seen it already. So there's no problem if you have not seen, or if you are not if you don't know. I mean, I'm not expecting you to construct a proof right now, just in 1 minute or half a minute. The question is just in case you have seen, you know, tell me, I'll then take it from there. Okay, so what you can do is the following. So let's forget about this nth term in general. Let's say let's look at S. So this is S0, S1, S2, S2. S2 is 1 plus half plus 1/3, right? Or maybe not S2. What I'll do is S3. Let me look at S3. So S3 is definitely bigger than this. So I have reduced this a little bit. I've made it 1/4. Okay. No, so this is equal to 1 plus half plus, now you put them together, what do you get? Half. Okay. Now I won't look at S4. I would look at a little further away, like 1 plus half plus 1/3 plus 1/4 plus okay, I'll go to, what is this? This is S7. S7. Okay, again here I'll use a similar kind of estimate. So I won't disturb the initial 2, that does not matter much. So 1/3 I'll replace it by 1/4. So I have strict inequality here. And this 1/5, 1/6, 1/7, I'll replace them all by 1/8, the last one. So I would have made the expression smaller. right? So this inequality is fine. This is a strict inequality. And what is the result here? 1 plus half plus, so these two together gives you half. These four together again gives you half. So you have 1 plus 3 times half now. Earlier it was 1 plus 2 times half. Okay. Next you look at S15. And you use a similar reasoning. So what you do is each term here you replace by 1/8, the last one. Each term here you replace by the last one, 1/4. Each term here you replace by the last term, the smallest one, that is 1/16. There are 8 terms here, there are 4 terms here, there are 2 terms here. So when you add them up, what you would get is 1 plus half, then another half, then another half, then another half. So that is 1 plus 4 times half. Okay. So now you can see the pattern, right? So the pattern is this. If you take the not the nth partial sum, but 2 to the power n minus 1th partial sum. So this is s 2 to the power 4 minus 1. The previous one was s 2 to the power 3 minus 1. This was s 2 square minus 1. So what you will get is, so I'll just write down the inequality. The proof is the same. You have to just so this is greater than equal to 1 plus n by 2. Okay. So for general nth partial sum, it may be difficult to handle that quantity. We may not be able to say something immediately, but these intermediate partial sums, they are easier to handle. And as you can see, you can immediately get these inequalities. But you also know that this is a series of positive terms. That means, in fact, they are all strictly positive. So you have strict inequality. Okay. And now what you have derived here is that S3 is bigger than 1 plus, what was it? S3 bigger than 1 plus 2 by 2. Then S7 was bigger than 1 plus 3 by 2. And then as you go further, S15, this is bigger than 1 plus 4 by 2, and so on. This is bigger than 1 plus n by 2. What will this tell you about the sequence Sn?
Not bounded above.
Yes, it is not bounded above, which means that this series diverges, right? And since this series diverges, if you are looking at, let's say, something like this, 2n plus 2. This series, that will also diverge, because this is nothing but half times the original series. This diverges, so this will diverge. to plus infinity. Similarly, if you look at this, so what would be the nth partial sum here? Nth partial sum here would be 1 by 3 plus 1 by 5 plus up to 1 by 2n plus 1, which is greater than 1 by 4 plus 1 by 6 plus 1 by 2n plus 2. So I have reduced each term a little bit. And this is, I'm adding half at the beginning. And then subtracting it. And we have just seen that this diverges. That means these go to plus infinity, which means this entire thing go to plus infinity. So this also diverges. Okay, so 1 by 2, 1 by 4, 1 by 6, that series diverges. 1 by 3, 1 by 5, the odd reciprocals of odd integers, that also diverges. Now let's go back to this series again. So here in this way of doing things, there would be a problem because this would go to infinity. This should also go to infinity as you keep increasing n. So this separating out plus and positive and negative things, that is not going to work. So we are again looking at this series. So what can we do? What else?
Take the sum of adjacent terms
Okay.
and see if there's some pattern or something. So like 1 is always greater than half, 1 by 3 is greater than 1 by 4.
So these would be positive, yes. But how to control meaning how to have an idea about the behavior of the entire sum. Okay, so let us so in what are the tools available if we want to see whether, say, Sn converges? So we are interested in this question, right? Whether this converges. Now, when you are interested in this question, what are the things that are available to us?
The necessary condition, but that is met. So,
Sorry?
like, one way to check in general if a series converges was the necessary condition that.
But yeah, that is
met.
necessary.
Yeah.
No, what I'm asking is forget about this series. Just so forget about this part of the screen now. Just focus on this statement. You have a sequence, and we are interested in the question whether this sequence converges. So go back to sequences. What are the tools, different tools that are available to us?
The Cauchy sequence.
Okay. So Cauchy was one, and other tool was if it was, say, monotone, etc. Here it is not monotone because alternately they go up, come down, go up, come down, right? Because the signs alternate. So monotonicity we cannot use here. Sn is not monotone. Cauchy is something which we can try. So let's try that. So let us do the following. So let's look at let's say S5 minus S9. So what shall we get? Or let me write it. It will not matter eventually because there will be a absolute value. So what is this quantity? So S5, the last term is minus 1 to the power 5, 1 over 6. So up to that term they cancel. So minus 1 to the power 6, 1 over 7. Okay, so this is the difference. Now if you take that out, it is just 1 by 7 minus 1 by 8 plus 1 by 9 minus 1 by 10. Okay. So now about this quantity, what can you say? So this is 1 by 7 minus 1 by, I'm just writing it slightly differently. Okay. Okay. So before that, let me just let's observe this, the following. You can write it as this plus okay, now this is non-negative, this is positive, this is also positive. That means you can actually get rid of the absolute value outside. So this is the same without that absolute value. This is fine. The expression inside, if we group them like this, both are positive quantities. So you can just get rid of the absolute value sign outside. Now the same quantity you write. So now we don't need to use the absolute value sign anymore. Only thing I'll do now is I'll just group them differently. Okay, we already know that this is positive. Now, writing it this way, what this will tell us is that this is less than 1 over 7. Right, so S9 minus S5 is less than 1 over 7. What would be the case if we had S10 minus S5? So here it would be the earlier expression and one more term. So I'll just copy paste from here so that I don't have to write all these again. And there will be another term. Again, you take out minus 1 to the power 6 outside. What you have is 1/7 minus 1/8 plus 1/9 minus 1/10 minus 1/11.
So +1 by 11.
Huh? Right. Plus, yes. Right. Thanks. Okay. So again, first, what you observe is if you group them like this, you'd be left with one, but that one would come with a plus sign. That means this is equal to, so you basically you need not use the absolute value sign. This is positive, right? Because the quantity inside is positive. Okay. And now you group them differently, just like you did earlier. And again, what this will tell you is that this is less than 1/7. Because this is positive, this is positive. That means you are reducing 1/7. You are subtracting some positive things from that. So that is be less than 1/7. Okay. So what you observe is this. If you have Sm plus n minus Sn, okay, now you have to do the whole thing with m and n instead of the specific values 5 and 10, 5 and 9, etc. So what you would be able to show is that this is going to be less than 1/, n plus 1 is gone, so n plus 2 for any m greater than equal to 1. Okay, so I'll just write down, I mean, it's the same argument. So you first write down the expression. So the expression that you will get is -1 to the power n plus 1 by 1/n plus 2 plus -1 to the power n plus 2 1/n plus 3 and so on. We'll go all the way up to -1 to the power m plus n by m plus n plus 1. Okay, so first step, you'd take out this out of the modulus sign. So what you will have is this. So here, sign of the last term would depend on the value of m. So that you have to write down and see whether it would be m or m plus 1. But now onwards, again, the argument would be the same. The first step, you'd observe that if you group them like this, it is a positive quantity. So you can get rid of the modulus sign, and then you group them slightly differently. So you keep the leading term separate and then group two at a time and conclude that this is less than equal to this leading term, which is 1/n plus 2. So you will get this inequality. And now once you have this inequality, you can use the Cauchy property, Cauchy criterion to claim, to prove that this sequence would converge. Okay, so this series is going to converge. So any questions from this proof?
What if n plus 1 is odd, then shouldn't it be minus?
No, so that's what. So I have covered both S10 minus S5 and S9 minus S5. You look at the two cases, you will see that whether m is odd or even, it will not matter.
Okay,
You
so n has to be.
Sorry.
So n, I didn't say m, I said like n.
N. No, n you are taking care of by taking this power out. Okay, so only the nature of m would affect the quantity inside once you have taken this leading sign out.
So I'm just saying, like, because the because n in the example was 5, the leading
Hmm,
quantity was positive. But if
No, no,
there's
no, no. But that's what. So if it was 6, so okay. What you do is, I'll suggest you do the same calculation with 6 instead of 5. You take 6.
yeah,
Okay, do that and see what happens for yourself.
like maybe we can take the second one as the leading one in that case.
Second one meaning.
So say if n was 6, then n plus 2 would be even now.
No, no, no. Don't change the order of the terms.
Okay.
Keep them in that order, because otherwise the other argument would get messed up.
Yeah.
Okay, what you use crucially here is that the terms, if you forget about the signs, they are decreasing. That is one crucial component in the argument. When
Yeah.
you're grouping them like this or like this, you are using the fact that the subsequent ones are smaller. Okay, so if you change the order, then that thing would get disturbed. So
Okay.
just do the computation with instead of S5, you take S6. So let's say S10 minus S6, S11 minus S6. Do it. You will see that everything is exactly identical. Nothing changes. Okay. Now, once you do that, so we'll take it a little further. Now let's look at a slightly more general situation, general series, where you have. So I'm not saying that this is 1 over n plus 1 anymore. What I'm saying is these CNs are positive, first of all, and these CNs are decreasing. Okay. So Cn is a monotone decreasing sequence that goes to 0. And we are looking at this series. Right, so that example was a special case of this, where Cn was 1 over n plus 1. But now we are looking at this slightly more general case. So Sn here is Sn here is C0 minus C1 plus C2 minus minus 1 to the power n Cn. Okay. Now we will see that exactly the same argument would go through for this case also. Why? Because, so let's look at this. So what is it? This is, so up to the nth term, all are cancelled. So you would only have the terms from the n plus 1th onwards. So n plus 1, Cn plus 1, plus n plus 2, Cn plus 2, plus there's a modulus sign, and the last term would be n plus m, Cn plus m. So the first thing to do, you take it out. Cn plus 1 minus Cn plus 2 plus Cn plus 3 minus Cn plus 4 ... So the last term is going to be so you have to check this part that I have written it correctly, because you are taking out minus 1 to the power n plus 1. What you are left with is minus 1 to the power m minus 1, which is the same as minus 1 to the power m plus 1. So I wrote m plus 1. Okay. So now the argument is exactly the same again. So you first pair them like this, starting from the first term. So each term is non-negative. And if you are left with a single term, that would come with a positive sign. So that is the other observation you have to make here. If a single term comes, because the first term has a positive sign in each group. So if there's one term, the second term missing at the end because of the parity of m, then it would come with a positive sign. So the entire quantity inside the modulus sign, that is going to be non-negative, which means you can get rid of the modulus sign. N plus 1, sorry, n plus 1. So you can get rid of the modulus sign. And once you have got rid of the modulus sign, now you group them differently. You keep it separate, then group these together, 2 at a time. And again, you will see that if at the end, if you have one term that will come with a minus sign, that means you are reducing further. So this whole thing would be less than Cn plus 1. Okay, so Sn plus m minus Sn in this case would be less than Cn plus 1. And again, use this and the fact that Cn goes to 0 to show that Sn is Cauchy, which means the series you are concerned with, that would converge. Okay, so what do you prove for that particular series, minus 1 to the power n, 1 over n plus 1? That is, in fact, a slightly more general fact. In fact, this is called Leibniz theorem. So this is such series are called alternating series. The signs are changing, alternating. So if the signs are changing, and if you observe that the nth term, the value, the absolute value, they are decreasing and they decrease to 0, then the series would converge. Okay, so any question? Okay, now next let us look at another very special type of series, which is, so let's say P is real. Let us look at this series. So let's say P is positive, not just real. So what can we say about this series? So what is the nth partial sum? You know the expression for this, right? It would be this if P is not 1, because if P is 1, then you have problem with this expression. But if P is 1, you can write down the expression for Sn straight away. This would be n plus 1. Okay. Now, what can you say about the convergence or divergence of this sequence Sn? So in this case, it would diverge to plus infinity, right? If P is 1, then Sn is n plus 1, and that diverges to plus infinity. Okay, now what about this case? So here it is So the behavior is basically going to be determined by the behavior of this sequence, p to the power n plus 1. Which is basically the same as the behavior of this. So what can we say about this quantity, the limit of this? This I did not mention in, yeah, sorry.
If P converges to 0, then this would converge to 1 upon
No,
1
P
minus.
P is a fixed number. P is a fixed number.
Sorry, P to the power n. Sorry, the limit.
No, so now what I'm asking is, what do we know about P to the power n?
So like if P to the power n is, so if P is greater than 1,
Okay.
then
If P is greater than 1, then?
then this will diverge to infinity.
Okay. And
So will Sn. So if P is less than 1, then this will converge to 0. Yeah.
0. And okay, so since we are only concerned about P not equal to 1, so this will cover everything. So about the series, what can we now say?
So if P is between 0 and 1, then this series should converge to 1 upon 1 minus P.
And
if it's greater than, it should diverge to infinity, plus infinity.
And in fact, when P equal to 1, then also, yes. Okay. Okay. Now, what if I allow P to be negative also? So I mentioned here that P is positive. Now let's say we allow P to be any real. Then any modifications? I mean, what happens for other values of P?
So sir, we should also like do in the negative side, we can like separate it between 0 to 1 and like 0 to minus 1.
Okay.
Less than 1.
Okay. So what would be the final thing?
So if P is between 1 and minus 1, then it should still be the same, I think.
Okay.
I think it should be this.
Okay, but there are other cases also. So this case it's already covered.
Yeah.
Now the other cases are the following: P equal to -1 and P less than -1. So anything about those cases?
So if P is equal to -1, and it will be 1 minus 1 plus 1 minus 1. It will depend upon, yeah, so it then we
does not have a limit, right? Okay.
Okay, so we're talking about P to the power n or summation P to the power n?
No, we are talking about this series.
Okay. Yeah,
So that is where we started with. Yeah.
Yeah, so it will be 0 or 1 or yeah.
So the series does not have a limit.
Yes.
And what about P less than -1?
Also don't know, because it can also go to minus infinity.
No, it does not go to minus infinity.
Okay, so
Again,
we'll have to do something similar to.
so the this would be the same. The behavior, it will not have a limit, but in this case, it would be slightly different from the behavior in this case. In this case, the partial sums are either 1 or minus 1. In this case, their magnitudes will, absolute values will keep increasing, but the signs will fluctuate. Right?
Okay, so it's like the opposite of what we did in the 1/1 n+1 case.
Opposite meaning?
It was like it was shrinking. Shrinking.
They won't shrink. They would expand, in fact, and with alternating signs, alternating. Like I mean, it won't be exactly equal to that, but something like n minus n, n+1, minus n minus 1, that kind of thing. So magnitudes, absolute values would keep increasing, but the signs will alternate. So it will not have a limit. So this again, since I'm not writing down the complete proof, you should try that. Try to write down proof. Okay, now just a definition. So suppose we are looking at this series summation n. Okay, so what we have defined is this series being convergent. The meaning of when do we say that this series is convergent? Now we say that this series converges absolutely if the series converges. Okay, so the series converges absolutely if not that series itself, but this series converges. So you are replacing the nth term, each term by its absolute value, you get another series. If that series converges, then you say that the original series converges absolutely. So for example, if we look at this series converges, but this series does not converge absolutely. Right? So the two notions are different. Does not converge absolutely because when you take the absolute values, you get that other series, summation 1 over k plus 1, and that we have seen diverges to plus infinity, does not converge. Whereas this series converges, that also we have seen. So here is a series that converges but does not converge absolutely. Okay, what about the opposite? If a series converges absolutely, does it converge? In other words, suppose converges. Now, does that imply that this series converges? So for this, you can look at the partial sum. So let's say Sn is the partial sum of this, A0 plus A1 plus up to An. Let's denote the partial sum of that series by Tn. So that is mod A0 plus mod A1 plus up to mod An. Okay, so what you are given is that Tn's converge. And what we have to check is whether Sn's converge. And again, since we have no information about the signs of the A0s, we cannot say anything about monotonicity of the Sn's. They can be positive, negative, anything. So what other tool do we have? The other tool that we have is the Cauchy criteria. Now, if we want to look at the Cauchy criteria, so that would be an plus 1 plus up to an plus m. Now, if you use triangle inequality, we separate them out completely. And now immediately we'll observe that this is nothing but Tn plus m minus Tn, which is also its absolute value because Tn's are increasing. Okay, now look at this inequality now. So from here and from the fact that Tn converges, so Tn is Cauchy. That means by taking n and m, n large enough and m anything, you can make this smaller than any epsilon that you are given. And because of this inequality, you can do the same for the sequence Sn also, which means that Sn is Cauchy. That means summation n converges. So the answer is that. Now I can remove this. I can remove this question mark. This statement that if a series converges absolutely, then it converges. Okay. Now, so before I end, I'll finish with one more property. It's very, very important property, but it's the proof is simple enough. So suppose you have two different series you are given. Okay. Now, what are the other information that we are given to begin with? Those are the following. This mod an is less than equal to bn for all n. Okay. So this is something that is given to us. And the other thing that we are given is that this series, the second series, the summation bn, that converges. Okay, so these are things that are given to us. Then this the first series will converge absolutely. Okay, the proof, and again, as I said, the proof is not difficult. So you look at the partial sum, a0 plus a1 plus up to an. You call the partial sum of the second series Tn. So this is b0 plus b1 plus to bn. And also we want one notation, un, let's denote by un the partial sums of this series, that is the absolute values of the ans. Okay, so now from the condition that you are given, you conclude that, so un plus m minus un, you show that.
So can we use the fact that so mod of an is a positive sequence, and AN is bounded because Bn is convergent and AN is less than Bn for all n. Then by the property that we did at the start of the class, that mod of AN is a convergent sequence, and then
no. Say it again once more.
So since mod of AN is less than or equal to Bn for all n, and since Bn is convergent, then mod of AN is bounded above.
Yes. Yeah.
And mod of Bn is also positive, so we can use that to say it is convergent.
Yes, you can use this. So here I was talking about the Cauchy criterion. What you are suggesting is so from the conditions, it follows that Bn's are all non-negative because of the inequality mod AN less than or equal to Bn. So this converges means that these partial sums, that is Tn bounded above. And from here, it would follow that the UNs bounded above. Which would give you that summation mod AN converges, which means AN converges absolutely, which is exactly the conclusion. This is what you are saying, right?
Yes.
Yeah. This would be a shorter proof, simpler proof. Yes. And if you want to go to Cauchy property, you can do that, but this would be simpler. So if you want to use Cauchy property, you have to go through these steps. So this inequality would give you, since this converges, the Tn converges, this is Cauchy. So this difference you can make small. By this inequality, you can make these differences small. So so UN would be Cauchy, which would mean summation AN would converge absolutely. So it won't be too much more complicated, but possibly this would be slightly simpler. So okay, so I think I'll stop here today. I'll continue with this statement and then go further from there. So this is part of what is known as comparison test. So basically, you know the behavior of one series and you are given another series. You compare them, the terms, and then you arrive at a conclusion about the series that you are interested in. So that's comparison test, and this is one part of the statement of that. So we'll look at one or two more tests for convergence, and then so what all these will help us do is, as I said in the beginning, this series that helps us talk about infinite sums. So, and that in turn will allow us to talk about various functions that we have you have encountered in the past. So it will allow us to give a precise definition of all those functions that we have come across, but we are not completely sure how to define them, etc. So it will give us a large supply of functions, which eventually are what we are interested in. Okay, so I'll stop here. Any questions? Anything you want to say? Okay, so if not, then see you next week. I'll disconnect now.
Thank you, sir.